Welcome to today's lecture, friends. We'll look at an important concept today, kinetic equilibrium. It plays an important role in the context of the thermal history of the universe. What is kinetic equilibrium? Kinetic equilibrium, if a species in the thermal mixture is the mixture that contains all sorts of species. If a species which is present in the thermal mixture has the distribution function that has a particular kind of expression, and that expression is Fermi-Dirac for fermions, Bose-Einstein for bosons. So for Fermi-Dirac distribution we have this formula. For Bose-Einstein distribution, which is for bosons, we have this formula. We'll talk more about kinetic equilibrium when we will study Boltzmann equations. And now once the distribution function is given by this formula, then let us recall the expressions that we looked last time. The expressions for the number density, for the energy density, and for the pressure. So these are the expressions that we saw last time. They all depend upon the distribution function, and if the distribution function is given by this formula, that is when the species is in kinetic equilibrium, then we take this formula for distribution function, we plug this formula here into the expressions for the number density, for the energy density, and for the pressure. And will there be cases when a species is not in kinetic equilibrium? Yes, we will study that there will be scenarios when a species is not in kinetic equilibrium, but for the most part of the evolution of the universe, or at least you can say that when we are performing analytic calculations, then we will use this approximation of kinetic equilibrium. So this may be valid for a large part of the evolution history of the universe. This may be an approximation, but it is a good approximation. We will see why it is a good approximation when we will study Boltzmann equations. But for now, let us assume that every species is obeying this kinetic equilibrium, so that we can take this expression for the distribution function, plug the expression for the distribution function into the expressions for the number density, energy density, and pressure, and then we'll go from there and calculate the expressions for these three equations for different types of species. That's all for today. Thanks for watching.